Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 70. It's on solubility. You've probably noticed that if we add salt to water, it will dissolve. But if we add more salt and more salt and more salt, eventually it doesn't dissolve anymore. And so what's going on? Well, if we look down at the atomic level, we're adding a salt grain, and that's made up of all these ionic bonds, sodium and chloride, and they're going to break apart into their aqueous ions. They're going to be ushered away by the water. That's going to increase the concentration of those ions in solution. And so if we increase the amount of ions, eventually no more ions can be added. And so that's going to push it back to this more solid form of salt. And so if we look at a solution, remember we're dissolving a solute in a solvent. And so you can think of that solute as a solid if it's all chemically bonded together. And if we can break it apart into its ions, then it's dissolved in solution. And so if we think of on the left side of our equation, we have the solid form, and on the right side, we have it broken apart into its ions. And so really in a solution, we have a reversible reaction. It's going to have its own equilibrium constant, and we'll call that KSP, which is essentially the solubility product constant. And that's a way to measure the solubility of any kind of a salt. And so there are a few things that are going to affect the solubility. One of the big ones is going to be delta G. In other words, it's going to be the enthalpy, it's going to be the entropy of the system. Let's say that there are really intense bonds between these in the solid form. It's going to be hard for those to break apart into their ions. Likewise, as we change what is in the solvent, if we add more ions to it, it's harder for more ions to be added. We could also change the pH, and that's going to affect what can be dissolved as well. Now, there are a few things that dissolve readily in water that you should simply know. Those are going to be the ammonium ions, potassium ions, sodium ions, and then also the nitrate anion as well. And so if we look at sodium chloride breaking down in water as a reversible reaction, on the left side we're going to have the solid form, on the right side we're going to have the two ions that are in aqueous environment. Remember, we're breaking those apart. A wonderful simulation to look at this is the PHET on salts and solubility. And so I'll put a link down below, but basically I'm going to add a little bit of salt, and we're going to look at this at the atomic level. And so what's going to happen is the water's ushering those ions away. And so we're going to break it apart into its cation and its anion. Let's say I radically increase the number of ions. What's going to happen? Well, you can see that most of them are going to be in solution, but some are going to go back to that solid form. There's simply too many ions out there. And so we've pushed it more towards the right side of this reversible reaction. Now let's look at a different salt. So now we've got silver bromide. If I were to add 200 of the cations to this, we're going to see a different kind of an effect. What's happening is that they're all going back to that solid form. So if we were to look at this equation up here, it's shifting it back more towards the left. And so how do we measure, does a reaction go to the right or does it go to the left? Remember, that's going to be our equilibrium constant. And so if we look at the equilibrium constant of sodium chloride being dissolved in water, we could set it up like this, where it's going to be the concentration, remember, of the two products over the concentration of that reactant. Now we can get rid of that reactant since it's a solid, so our KSP value is going to be 37.3. What does that mean? Since it's much greater than 1, that's going to shift it way towards the right. We're going to have way more of those ions. If we compare that to the silver bromide, what's our KSP value here? It's going to be much less than 1. What does that mean? Our equation is going to be shifted way towards the left, and so we're going to have more of that solid form. And so the neat thing about this simulation is you can play around with the KSP values. Now I've got a theoretical salt with cations and anions, and I'm simply going to lower the KSP value. You can see as I lower it, it's starting to move back more towards the left. It's moving back more towards that solid form. So if you have a really low KSP value, it's going to be shifted towards the left. If I radically increase KSP, then it goes way back more towards the right, or in aqueous solution. And so that's what KSP affects, but you should be thinking, like, why does it affect that? What affects KSP? Well, it's mostly going to be delta G, so changes in enthalpy and changes in entropy. And so if we look at the solid form, remember there are going to be ionic bonds between all of these, and the greater those bonds are, it's harder to break them apart and then move it away into solution. And so also there are going to be interactions. Once it does get broken away, it's going to interact with the solvent itself. And let's say there are already a lot of ions in solution, it's harder to be added. And we could also change, for example, the pH of that solution increase or decrease the number of protons, and that's also going to change how it interacts with the solvent. Now, we basically just talked about enthalpy. Remember, entropy is going to be an important part of this as well, and that's why it's better to look at the whole delta G. And so what are some applications of this? Well, let's say we have seawater and fresh water, and we're going to try to dissolve salts in each of those. It's going to be different because in seawater, we're going to have all of these ions already present. Sodium, chloride, sulfate, magnesium, all of these are already there, and so it's hard for us to add more of those salts into solution. What's another application of this? Acid mine drainage. So how did this get so nasty? Well, there was probably a coal mine at some point that had a lot of sulfur in it, which combined with water and made sulfuric acid. And as it drained through this area, that decreased the pH, and so there's all of a sudden a lot of ions in solution, mostly iron hydroxide. What happens as it's now settled out is we're adding more fresh water to it. It's increasing the pH at this point. We can't hold those in solution, and now all of these ions, all this nasty iron is coming out of solution. Or we could look at acid rain. What's happening there is we're decreasing the pH, and that changes the amount of carbonate that we can actually dissolve. And so did you learn to predict the solubility of a salt or rank its solubility given the KSP values? Remember, the lower it is, the more likely it's be in the solid form or shifted more towards the left. The greater it is, the more it's shifting towards the right. Also, could you interpret data based on a KSP value? How is that going to behave? And then finally, can you look at what's going on inside the solid and inside the ions in relation to the solvent to predict our KSP values? I hope so, and I hope that was helpful.